In the previous lesson, we learned how to compute wide heteroskedasticity robust standard errors for regression coefficients. Those robust standard errors correct the variance estimates when the error variance is not constant. However, they do not change the regression coefficients themselves. The regression line estimated by ordinary least squares remains exactly the same. In this lesson, we study a different approach to heteroskedasticity, weighted least squares, often called WLS. Unlike White's estimator, weighted least squares actually changes the regression estimation by assigning different weights to different observations. We will compare three methods: ordinary least squares, White robust standard errors, and weighted least squares. We will compare them algebraically, numerically, and graphically. Consider the scatter plot of our simulated data set. You can see that the spread of the points increases as x becomes larger. This pattern is called heteroskedasticity. Under the classical regression assumptions, the variance of the error term is constant. But here, the variance clearly grows with x. In our example, we assume the error variance is proportional to x squared. This means observations with larger values of x tend to have larger and more volatile errors.
Let us first estimate the regression using ordinary least squares. Ordinary least squares minimizes the sum of squared residuals, treating every observation equally. The estimated regression line is y hat equals 2.39 plus 1.34 times x. This is the OLS regression line. Under the assumption of homoskedastic errors, the variance of the estimated coefficients is sigma squared multiplied by the inverse of x prime x. But when heteroskedasticity is present, this variance formula becomes incorrect. To address this problem, Halbert White proposed a heteroskedasticity consistent covariance estimator. This estimator replaces the single constant variance with a diagonal matrix of squared residuals. The resulting variance formula is often called the sandwich estimator. The outer matrices form the bread, and the middle matrix forms the meat. Importantly, White's estimator does not change the estimated regression coefficients. The regression line remains exactly the same as the OLS line. What changes are the standard errors, which are now robust to heteroskedasticity. This allows us to conduct valid statistical inference even when the error variance is unequal.
Now we consider weighted least squares. The idea behind WLS is simple. Observations with larger error variance contain less reliable information, so they should receive smaller weights. Observations with smaller error variance contain more precise information, so they should receive larger weights. So, if variance increases with higher values of x, the weights must decrease as x increases. In other words, the weight assigned to each observation is inversely proportional to the variance of its error term. In our data, we assume that the variance of the error term is proportional to x squared. Therefore, the optimal weights are proportional to 1 over x squared. The first step in the WLS estimation method is to define these weights. Since we generated the dependent variable using heteroskedastic errors, by multiplying the explanatory variable with random noise, the error variance is proportional to the square of x. So in Mathematica, we define a vector of weights, called weights known, where each weight is equal to 1 divided by x squared. Next, we construct a diagonal weight matrix. This is a square matrix with the weights on the diagonal and zeros elsewhere. Weighted least squares then minimizes the weighted sum of squared residuals. The WLS estimator equals the inverse of the design matrix transpose multiplied by the diagonal weight matrix and the design matrix, then multiplied by the design matrix transpose, the diagonal weight matrix, and the dependent variable vector. Here, the diagonal weight matrix assigns smaller weights to observations with larger error variance. This changes the regression estimation itself. As a result, the estimated coefficients differ from those obtained using ordinary least squares. In our case, the ordinary least squares regression line has an intercept of approximately 2.39, and a slope of approximately 1.34. The weighted least squares regression produces a lower intercept and a steeper slope. This happens because WLS reduces the influence of observations with large error variance. In our data set, observations with larger values of x are much noisier. Ordinary least squares treats these noisy observations equally, which tends to flatten the regression slope. Weighted least squares gives less importance to these noisy points. As a result, the estimated relationship between x and y becomes stronger and steeper. The key insight is that these three methods solve different problems. Ordinary least squares estimates the regression line under the assumption of constant error variance. White robust standard errors keep the same regression line but adjust the standard errors used for inference. Weighted least squares goes further. It changes the regression estimation itself by weighting observations according to their error variance. When the structure of heteroskedasticity is correctly specified, WLS produces more efficient coefficient estimates and smaller standard errors. To summarize, ordinary least squares assumes constant error variance. White robust standard errors correct inference under heteroskedasticity. Weighted least squares improves estimation by reweighting observations. In practice, economists often use robust standard errors when the form of heteroskedasticity is unknown. But when the variance structure is known or can be modeled, weighted least squares can provide more efficient estimates. In the next lesson, we will consider the case where the variance is unknown, and introduce feasible weighted least squares.